Welcome, folks. Video discussing logarithms, exponentials, and other inverses. In this video, we're going to be talking about the natural exponent. So here's some motivation for this section. We just talked about the natural log of x, and I want to point out that the graph of the natural log of x passes a horizontal line test. Of course, the natural log has domain x greater than 0 and range y achieves all real numbers. Since the graph of that function passes a horizontal line test, the natural log function has an inverse. And the graph of that inverse is again found by rotating or reflecting the graph of the natural log function about the line y equals x. So the inverse function has domain x less than or equal to infinity, x between infinity and minus infinity, and the range is y greater than or equal to 0. So as we'll see in a minute, the inverse of this natural log function ends up being a special function called the natural exponential, and we'll talk about that for a second and then talk about how to do calculus on that natural log function. So here's the natural exponent, or I call it the exponential function. The exponential function of x is e to the x, and it's defined as the inverse function of the logarithm of x. So we have these two inverse relationships, that the natural log of e to the x is x for all x. E to the natural log x is x whenever x is a positive number. In addition, there are some known values of e to the x that we obtain from our known values of the natural log of x. Since natural log of 1 is 0, e to the 0 is 1. And since natural log of e is 1, e to the 1 is just e. And again, that number is e is 2.7, blah, 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 blah. And finally, the end behavior here, the exponential function goes to infinity as x goes to infinity, and the exponential function goes to 0 as x goes to negative infinity. So we'll see how to use this end behavior in order to evaluate a couple limits. So here's a limit. Let's go ahead and look at the limit as x goes to infinity of e to the 2x over 3 times e to the 2x plus 1. And a couple keys here. Exponential functions can be manipulated like usual, and e to the stuff goes to 0 as that stuff goes to negative infinity. So here we'll try to go ahead and multiply numerator and denominator of this quotient by the biggest exponential in the denominator, the reciprocal of that, which is e to the 2x, or e to the minus 2x in this case, as we'll see. So we can see that the quotient e to the 2x over 3 e to the 2x plus 1 can be written as 1 over 3 e to the minus 2x. So now evaluating the limit becomes quick because e to the negative stuff goes to infinity, goes to 0 as the stuff goes to infinity, or similarly, e to the stuff goes to 0 as the stuff goes to minus infinity. The limit in this case is just 1/3. Let's look at one more example. Here's one more example. The limit as x goes to minus infinity of e to the x plus e to the minus x over e to the x plus minus e to the minus x. In this case, since x is going to infinity, we need positive, since x is going to minus infinity, we need positive exponentials. So we'll go ahead and multiply numerator and denominator by e to the positive x. So again, here we're dividing by the largest e to the x power, or multiplying by e to the x in this case, because x is going to minus infinity. We see that e to the 2x goes to 0 as x goes to minus infinity, and we're left in this case with minus 1. Okay, let's go ahead and look at calculus on this natural exponential function. Properties of the inverse and the derivative of the natural logarithm can be used to find the derivative of the natural exponential. So we'll go ahead and do this using our relationship y equals e to the x, and then the corresponding inverse relationship, which is x equals natural log of y. So again, given y equals e to the x, we know that x equals the natural log of y. We can use implicit differentiation here to find that the derivative of x, of course, is 1, and the derivative of the natural log of y is 1 over y dy dx. Now we'll just solve for dy dx and keep in mind that y was originally e to the x. So this is pretty amazing, actually. The derivative of e to the x is just itself e to the x. So here are our differentiation rules for the exponential function. The base derivative, the derivative of e to the x is e to the x, and of course the chain rule, if there's e to a composition, the derivative of e to the composition is e to the u times the derivative of u du dx. Okay, let's go ahead and have a look at a couple examples. Here's the first one. Let's find the derivative of e to the minus x squared. This is just a simple application of our new derivative in the chain rule. In this case, the derivative f prime of x is minus 2x times e to the minus x squared. A couple comments here. It's common to write powers of x in front of the exponential function, and also it's common to write exponential functions involving things that aren't plain old x as exp of stuff. Okay, this is something that came up as a result of old typesetting questions, that it was hard to take exponentials of exponentials. So you'll sometimes see e to the minus x squared as exp of minus x squared. Okay, let's look at another example. Here's another example. Let's find the derivative of e to the minus 2x times cosine of 3x. And when you take a 30,000 foot view of this problem, you can imagine that you'll have to use a product rule and then the derivative of our new function, the exponential function. So I've written the product rule out here in all of its glory. The first function times the derivative of the second plus the derivative of the first times the second. A chain rule in both those derivative cases, the derivative of cosine 3x and e to the minus 2x both requires a chain rule. And then I'll go ahead and just simplify this by factoring the exponential quantity. So here's that derivative in all of its glory with a big minus sign out front. E to the minus 2x times quantity 3 sine of 3x plus 2 cosine of 3x. Let's do one more example. Let's find the equation of the line tangent to y equals e to the x at x equals 0. Now everybody knows that you need two things to write down the equation of a line. We need the point and the slope. We can see here that when x is equal to 0, y is equal to 1. That gives us the point. And then everybody also knows that in the case of a tangent line, the special thing about a line tangent to a graph is that the slope of that tangent line is given by the derivative of the function. Of course, in this case, the derivative dy dx is just e to the x, and e to the x at x equals 0 is 1, so the slope of the function is 1. So we can quickly write down the equation of the line tangent to the curve at x equals 0. That tangent line is just y equals x plus 1. So as we'll see in a little while, this happens to be a special tangent line, and we'll come back to this later on. Okay, here's the general antiderivative rule associated with this derivative rule. The general antiderivative of e to the x is e to the x plus a constant. Let's look at a couple examples. Here's the first one. Evaluate the integral e to the 4x dx. So here we'll go ahead and use a simple u substitution to simplify the integrand. So here's our simple u substitution, u equals 4x, giving us du equals 4 dx, or dx is 1/4 du. Rewriting the indefinite integral in u world, we can see that we end up with 1/4 times the integral of e to the u du, which is just 1/4 e to the u. And back to x world, 1/4 e to the 4x plus a constant. Now, these type of simple u substitutions are going to become more routine for you soon, and you'll sort of get used to the form that these simple u substitutions take, just like with cosine and sine. Here's another example. Let's go ahead and evaluate the integral x e to the minus x squared dx. So here we'll go ahead and try the u substitution, u equals negative x squared. Okay, the u substitution in this case is pretty quick too. Rewriting the integral as minus 1 half e to the u du, we can see that the indefinite integral is minus 1/2 e to the u plus a constant, which back into x world is minus 1/2 e to the minus x squared plus a constant. And again, just like always, we can check these indefinite integrals by differentiating, and you can imagine doing the derivative here. It's one we did earlier. Okay, one more example. The definite integral from 0 to 1 of e to the minus 3x dx. And I'll go ahead and use a u substitution here to evaluate this definite integral. So the substitution again is quick in this case, and here we'll also substitute our limits. When x is 0, u is 0, and when x is equal to 1, u is minus 3. So I've rewritten the definite integral in u world and then used just a couple properties of definite integrals to simplify, pulling out the constant and then using the minus sign to swap the limits of integration. Of course, the definite integral of e to the u du from minus 3 to 0 is just e to the u from minus 3 to 0. So we evaluate that, and the answer is 1 minus e to the minus 3 all divided by 3. Okay, folks, hope you've enjoyed this video on the natural exponential function. Have a great day, and we'll see you next time. Bye-bye.